presented the foundation of the whole Newtonian formalism. Nothing else needs to be added. So now we're at the point where we can start building, right, applying that foundation for this system, for that system, searching for some shortcuts, right, some simplifications, right. So now we'll start building this castle. But although we introduced Newton's third law, but we still didn't see the actual beauty of having that Newton's third law in this picture, in the classical mechanics. Right? So, in order to see the beauty of that law, we started discussing multi-particle system. So basically we started moving from the foundation in the first to the first point. What if we have many particles, not just one particle? So what can be done in this system? And again, as I said, it will help us to see the advantage of having Newton's third law. Okay, we stopped somewhere up here, right? So I just presented the system. We have multi-particle system. Interacting particles. They interact, so there are internal forces, and we assume that they obey Newton's third law. It's a very important assumption, and the only assumption. Right. And particles alpha runs from 1 to n, so then of course internal forces, I label it as F alpha beta, completely arbitrary particle beta, completely arbitrary particle I alpha. Right. And then of course the whole system might be exposed to some external force. I label it as external F alpha, so it's a force, external force acting on this particular particle alpha. And you see a bunch of dots, so those are particles. Okay, so now, and of course we assume that we use inertial reference frame, because without that we wouldn't be able to use Newton's second law, period, right? So every time we have to use inertial. Right, so now let's write down, let's apply Newton's second law for the first particle, not for the first, for particle alpha. Right? Okay, so I will write as F, which way I label it? Just F alpha. It's a net force acting on particle alpha, which consists of internal and external. And of course, that inside of this we have, why not? F alpha beta, so I'm just summing all forces, because internal force can come from that particle, from all particles, right? Except, of course, summation over here from over beta from 1 to n, but we have to of course exclude alpha particle itself, because the point cannot exert force on itself. So we have to exclude that from this summation. So beta is not equal to alpha. So we sum over the whole system, but of course except for alpha particle itself. And of course there is an external force, plus F alpha external. And so that's just a net force, but of course according to the Newton's second law, application for a point mass in the inertial reference frame. Okay, let me remove this mass, this particle. So it must be equal to the rate of change of the linear momentum of that particular particle alpha. Right? Okay, so we just apply Newton's second law, use this fact. Right, but we have multi-particle. Let's just look at the whole picture. Let's just look at the total linear momentum of the system. Total linear momentum. Right. And I will use P capital. In order to see the difference between P small and P capital, I put this bar underneath. If there is this line underneath, right, so it means P capital. This without, it means P small. Right? Because I remember when I was taking class, it was a big issue for me to see where is the capital, where is the small p. Right, so as a result, of course, P equals, it's a summation over all linear momenta, right? Of course, summation from 1 to n. And we want to know more. We want to see what happens with this total linear momentum in time. What about dynamics of the total linear momentum? Alright, so let's look at the rate of change, P dot. Of course, it is equal to summation over alpha from 1 to n, P alpha small dot. Okay? And now we'll grab this P alpha and substitute it. Of course, you will end up with, so here summation over alpha. Let me first write this term, right? External forces. So we'll have summation over alpha, F alpha external. So it's this. And then of course now we have here we have summation over beta, and here summation over alpha. So we'll have double sum plus summation over alpha, summation over beta of f alpha beta. That's it, right? Of course, here again summation from 1 to n. Of course, here beta is not equals to alpha. Alright, so that's what we have, and now let's try to understand what's the story. With these terms, everything is simple. It's just a net external force. So nothing interesting, right? It's just a net external force. But what about these? Who knows? Let's look closer. Let's look deeper at that term about this question. Right. So I will probably do it here. Right. I will just look at this term. Right. So.
Excuse me, Professor?
Yeah.
I can't see the screen. It's almost like kind of blur.
Really blur?
Blurry for me as well.
Same for me. I haven't been able to see anything very well you've written down.
What can be done? Are you using Wi-Fi or cables?
Okay,
Wi-Fi.
I just moved closer to my modem and it didn't
I would
change much.
recommend to use just a cable, right? So again, my friend who's IT expert, right? So he said immediately ditch Wi-Fi, right? So use cable. So I'm connecting it through the cable. So I cannot think of what can be done. So everyone experiencing the trouble seeing this?
No, I can see it.
I can see it fine too.
I can see it fine.
Yeah, it's okay. We cannot do. It's internet quality. It's internet quality, and most likely it's on your side, right? And even it's even on TV. Some when they try to connect some reporters, sometimes they lose connection, right? So. Okay, the only suggestion, don't use definitely Wi-Fi. Right, use the cable.
This is all going to be in the book too, right?
Okay, I'm recording it. And actually I'm looking at you and you're also kind of blurry. Really blurry, although you're sitting right in front of the camera.
Yeah.
So I
that's
think it's your internet quality, right? You can check the speed, right? I forgot the website where you can go to check the speed. Right. I'm sure that guys right how to check the speed. I forgot. Okay, all right. I will try to write bigger, although if it helps. So this term. Let's try to see what we're going to get from that term. Okay, now double sum, I will just combine it as, I will write summation over alpha and beta, right? And now I will start doing some finicky things, right? I will take this f alpha beta and add exactly the same bunch of terms f alpha betas. But in order to avoid you screaming at me, I'm going to take and add 1 over 2. So I just added exactly the same set of terms. And of course divided by 2 so that it would be equal to that. Right? So it's illegal. It's legal. Alright, then in the second sum, what I'm going to do, these indices inside, they live only inside of this summation, so they don't go outside. If it happens, we call these indices a dummy indices, right? And you can do whatever you feel like doing with them. You can change their names, right? Who cares, since they don't go outside? It's sort of like in a country, right? Let's think about some closed country, really. It's sort of like a North Korea, right? So if they don't go outside, who cares what's their names, right? So they live inside, right? They can change their names, right? Whatever they want to do. But if they want to go outside, of course, You have to keep track of their names, right? And you cannot change it just randomly, right? But if everything happens inside, like in this case, you can change these names to alpha and beta to anything. You can use your names, names of your friends, pets, right? So let's do this. Let's use that freedom. Okay, I will open my explanation box. The second sum, in the second sum, right, alpha is beta and beta is alpha. Since they are dummy, okay, let me write, so they are dummy indices. Since they are dummy indices. Right. It's a common trick in calculus, I'm sure that you've seen it before, right? Okay, so as a result, in this sum, this will be equal to f beta alpha, right? And okay, let me rewrite it. So it's 1 over 2 summation f alpha beta plus f beta alpha vectors. Now it's time to use our assumption, because we used almost everything except for the assumption about the Newton's third law. Now we can use that. So again, I will open my explanation box, and now Newton's third law. So f alpha, oh no, let me use f beta alpha. F beta alpha equals to, of course, minus f alpha beta. So this term equals to minus f alpha beta. This is plus f alpha beta. And these two terms cancel each other. As a result, we're ending up with 0. So this double sum is 0. As a result, we can write that this rate of change of the total linear momentum equals to, this is 0, and this is just the net external force acting on the whole system, because we summed up over all these external forces. F alpha external. Okay, and we're getting to a very, very important conclusion. Internal forces disappeared. Internal forces are washed out completely. So it means that since they are disappeared, right, and here it's a rate of change of the linear momentum, total linear momentum, it means what? It means that the internal forces are not capable of changing the total linear momentum of the system. No way. So if you want to change the total linear momentum of the system, you have to apply external forces, right? And of course, consequences, we used it from the very beginning in physics 1. You remember when we were describing the motion, parabolic motion of the ball, for example, right, in the field of gravity. Although it's not a point mass, it's a multi-particle system which consists of gazillion number of points. And there are, of course, inside of tons of internal forces. But because of this, because all those internal forces obey Newton's third law, all those internal forces, they just cancel each other, brutally cancel each other, giving you 0, and as a result they are not capable of changing total linear momentum. That's why when we described the motion of the ball, we just looked only at the external forces, I know some gravity, gravitational force, air resistance, in order to describe the motion of this. Although, of course, it's a multi-particle system. So the beauty, and again, what we've used here in this derivation, only one thing: Newton's third law, and then some logic, some calculus stuff, right? But from the physical point of view, we used only one: Newton's third law, and it helps us to remove all the internal forces. That's the beauty, that's the advantage of having Newton's third law in our game, in this classical mechanics. If you have Newton's third law, if you have multi-particle system, and if you are interested in the motion of that multi-particle system as a whole, you can forget about internal forces. It's a tremendous simplification. And that's the beauty of having Newton's third law, that it allows you to wash out all the internal forces, because otherwise it will be a crazy problem, right? And another example, again, the same, let's say the same ball, right? So right now it's resting on my hand, right? In my hand. What's the total linear momentum right now? 0, right? Total linear momentum is 0. And of course we know that in order to change the total linear momentum, I have to apply external force, like push it, right? But by itself, because again, inside of that there are tons of internal forces, but they're not capable of changing this, in this case, 0 linear momentum, total linear momentum. If it was possible, right, I would get really scared, right, if out of the blue this ball would start rolling. It would be a really scary experience, right? But it's impossible because internal forces, they cannot change the total linear momentum. It's a very, very important conclusion because it simplifies work with a multi-particle system, any multi-particle system. All right, let me check what another thing. Then okay, then what's a role of internal forces in a multi-particle system? Okay, they cannot change the total linear momentum. Only external forces can do that. So then what's the role of internal forces in the multi-particle system? And in order to understand it, I'll give you a simple example of collision of two balls. Let's say identical. So let's assume that first one, I need some pedestal, you know, for demonstrations over here. All right, so but anyway, let's assume that this ball is at rest. And this ball is moving, rolling towards collision. So since this is at rest, so where is the total linear momentum of the system? Of course in this ball, which is rolling, because this is at rest. So total linear momentum is here. But then after collision, let's say they collide and now this ball starts rolling. So now the total linear momentum is still the same because it's conserved. Okay. Let's assume it's conserved, right? So it's still the same, but now linear momentum is here as well as there. So basically during the collision, linear momentum was shared. This ball shared linear momentum with that ball, and now they both have some linear momentum and they move together. Who or what helped to share linear momentum within the system? Internal forces. During the collision, internal forces, that's their role. Internal forces allows us to share linear momentum within the system. Okay, you're good, here's for you. You're bad, no, you're not going to get anything. So basically within the system, internal forces are sharing linear momentum. But of course, the total linear momentum, they're not capable of changing. You have to apply external force. It's sort of like internal forces. It's sort of like a work of a government in the country. Of course, in ideal world, government are not making any money. They're just a bunch of managers hired by the people to manage the work in the country, right? Their role is to collect taxes, some amount of money, right? And then redistribute. Okay, you've been good, right? So here's some money for you, right? You've been bad, you didn't vote for us, you're not going to get anything, right? So, of course, I'm joking with something like this, right? So, yeah, it's like government. Government is not making money. Corporations are making money, right? Trading, so external forces. Right? So again, so the beauty of Newton's third law, that it allows us to forget about internal forces if you work with a multi-particle system. Okay, so that's why I digressed a little bit immediately from our foundation in order to prove. And of course now immediately the conclusion out of this, right? If net external force equals 0, then it leads to the conservation of linear momentum. Conservation of linear momentum of the system, right? Okay, important conclusion. Let me put a new bullet. If net external force equals 0, then linear momentum is conserved. Conservation of linear momentum. Very important, of course, conclusion. And of course, guys, never forget that it's a consequence of the fact that external forces, net external force equals 0. Most of you will go through the grad school and qualifier exam, and not very often, but from time to time, students try to use, I don't know, conservation of something, and you ask, so can you justify why is linear momentum conserved? And I heard some answers like, it is conserved just because it is conserved. Or something like linear momentum is conserved because energy is conserved. I've heard even something like this, right? No, guys. You have to. This is some foundations, basically alphabet. Linear momentum is conserved because the net external force in a certain direction, for example, if linear momentum in the x direction is conserved because net external force in that direction is 0, or in the y direction, right? That's something fundamental which everyone, of course, should remember, should be aware of. Right. Yeah, another thing, sort of like a more philosophical. So in order to come to this conservation of linear momentum, again, effectively we just use, in terms of physics, only Newton's third law. As a result, physicists very often say that conservation of linear momentum is equivalent to Newton's third law, or Newton's third law is equivalent to conservation of linear momentum. For example, like when you discuss or describe motion over a rocket, you can do it easily either using Newton's third law, right? So you push something and that something pushes you back, or you can use conservation of linear momentum, basically equivalently strong descriptions. Right? Now let's write down all these advantages of each Newton's laws, because it's important, right? And then we will start applying Newton's second law, because that's the most important, right? Which allows us to describe motion of any system, first in Cartesian coordinate and then polar coordinate, couple of examples, right? But first, about the beauties. Right, so Newton's first law, I will just rewrite from my notes, right? So it helps to define and find inertial frames, where Newton's second law has that simple form. Okay, let me move this all to here. So, first bullet. So, Newton's first law, right, helps to, define. Okay, let me write, helps to find, but of course it can be used also to define, helps to find the inertial frames. Inertial frames where Newton's second law, has that simple form, where Newton's second law has that simple form. Yeah, F equals ma, running out of space. So that's the beauty of first law. Now let me change order. Newton's third law, right, was just discussed. It helps us to sort out the internal forces in multi-particle system. Newton's third law helps to sort out the internal forces. As a result, description of a multi-particle system is simplified tremendously. And of course, Newton's second law, it's the most important. It allows us to describe the motion of any classical mechanical system. Any, no restrictions. Again, classical system. Just equation of motion. Newton's second law, of course, is used to find the motion of the object. Is used to find the motion of an object. Of a system object, right? Okay. And on purpose I wrote down Newton's second law as the last one, because now I sort of logically start. First I write it in Cartesian coordinates, one example, and then we will spend quite some time rewriting it in polar coordinates, right? Okay, so Cartesian. In Cartesian. No, you know what? Let me first write, of course, Newton's second law, F, okay, I will use it like this, M equals to mr double dot. Of course, this is, it's a universal law, and then you can write it in any coordinate system, right, in any reference, or Cartesian, polar, spherical, elliptical, whatever you feel like. Right now, it's just a law, right? And now, of course, Cartesian coordinates. In Cartesian coordinates, of course, it's trivial. Right, of course, we will get that mx double dot equals to fx, my double dot equals to fy, and of course the same in the z direction, right? Okay, so in Cartesian it's trivial, but again, as I said, in polar we will spend like 10, maybe 15 minutes to write this properly, because there it's trivial. And that's one of the disadvantages of Newtonian approach. If you do decide to change coordinate system from Cartesian, it can be really, really painful to move to this coordinate system, right? Because you'll have to derive. But in the Lagrangian formalism, exactly the same form of the Lagrange equation. It doesn't matter which coordinate system you pick. It's significant simplification. Okay, so now let's look at one example. It's basically physics 1 example, right? But every time I feel like ditching it, but I couldn't convince myself, cannot, right? Because in a few classes we will solve the same problem using different approach, and it's good to sort of juxtapose them and to tell what's the advantage of having this method and what's the advantage of having that method. Although the problem is simple. Inclined plane, you release the box slide, you need to find how position of the box relative to the inclined plane. It's a physics 1, right? You solved it many times. But again, in order to compare it with different method, it's better to use some simple examples, right? Right, so now it's example 1.1. And of course I will move faster over here because it's simple. Okay, I'll move over here. And so first, an inclined plane. Right, angle of inclination is given, let's say theta. A box released from this point, so let's say, so we have a box is released. So basically at the initial moment of time, t equals 0, initial conditions. Okay, I started writing, I wanted to write x equals 0, but I haven't introduced coordinate system. It's not a good idea, right? So first of all, coordinate system, and of course, yeah, we're going to treat it as a point mass, and since we're going to use Newton's second law, the coordinate system must be inertial, period. Which one, of course, it's up to you, but of course the most convenient is x-axis along the incline. Right. And again, the origin will be is at the point of release. Right. So it means that at the initial moment of time, the coordinates were 0 and velocities were 0, since we assumed that it is released, or it was released. Right. Initial conditions. There is a friction. What else? Yeah, we need to find basically x as a function of time, right? So basically we want to describe the motion of this block. Right, so coordinate system is there, so we need to complete free body diagram. We need to introduce all the forces, because forces are one of the essential parts of the Newtonian formalism. So, of course, there will be normal force, gravity, mg, and of course, since there is a friction, so there will be a friction force F. Right, free body diagram. Of course, we'll have to decompose. This angle will be theta. Right. And I will start with the y direction. Newton's second law in the y direction. Right. Sum of the forces in the y direction equals my double dot. And of course you understand probably the reason why I started with the y direction, because it allows us to find normal force, and then normal force we need to find the friction force, right? It's just a logically better, sounds better, or looks better. So now at this point we need to apply something which we know. Otherwise, if we don't apply something which is obvious, we wouldn't be able to find nothing else. We wouldn't be able to find anything else. So in this case, we see that the block slides along the incline. It's obvious, right? So we're going to use that fact. That block doesn't move in the right direction, so y double dot equals 0. So we have to use that, otherwise we wouldn't be able to find normal force. Right? So our observation immediate that y double dot is 0. Right? And of course the net forces, it will be n is in the positive direction, and then in the negative direction component of this force, mg cosine theta, and it must be equal to 0. Okay, I don't like overlapping with this picture. Right, so of course normal force mg cosine theta, and of course we can find immediately the friction force. Coefficient of kinetic friction is given, right? So F will be equals mu n. This is not a vector equation, because again you understand, right? Normal force that way, friction that way, so it's not a vector equation. It's just a equation connecting absolute values of these forces, right? Magnitude, strength of these forces. So it will be mu mg cosine theta. Okay, so now we are ready to apply the second equation, of course. So let me put a bullet here. Now a bullet for the x component. So sum of the forces in the x direction equals mass times x double dot. In the x direction, this component of mg, it will be mg sine theta, and that component in the positive x direction. So it goes into the equation with plus. So it will be mg sine theta. Friction force, of course, in the opposite direction, so it will be minus mu mg cosine theta equals to mx double dot. Alright. And now mass can be murdered, mass murdering, mass destruction, right? And we're getting second order differential equation. So let me, you know what, no, I probably will be able to write a couple of more lines. So x double dot equals, g can be factored out, g sine theta minus mu cosine theta, trivial differential equation because right hand side is a constant, right? So we can easily integrate it. Right. X dot, you know what, no, I hate, I wouldn't be able to finish the problem over there, so I need to move up. You know what, I will move over here because I want to start the next thing. I want to start over here on the left side. So let me erase these beauties of Newton's laws. Right, so I will continue. Okay, maybe this line I can still fit. G sine theta minus mu cosine theta times t plus some constant, let's call it c1, but of course that constant is 0 because initial velocity is 0. We can easily apply initial conditions, so this will be 0. As a result, we can integrate it integrate it one more time. We will get x as a function of time. It will be g t squared over 2, and that bracket sine theta minus mu cosine theta, and again plus new constant, but again that constant again will be 0 because initial position is 0. Right? As a result, we're getting a function how x changes with time. So gt squared over 2 sine theta minus mu cosine theta. Okay, so again, as I said, in a few classes when we start discussing different approach, again we will solve this problem and then I will bring these results in order to compare that approach with this approach. Again, advantages, disadvantages. Although again, I strongly feel like every time I want, okay, I will dump this example because it's too simple, but because in order to compare those two approaches, I still cannot force myself to do that. Right, a special case, for example, right, so if theta equals pi over 2, for example, right, so basically you should get a free fall. If theta equals pi over 2, of course this is 0, this is 1, and of course x will be equal to gt squared over 2 as it should be for a free fall, because in that case it's not an inclined plane, it's a vertical plane, and of course the object will be flying, so matches. Good. Right. Again, in a few classes we will recall these results in order to compare. But for now, just application of Newton's second law, trivial application in this situation. Okay, now next. Again, now we will be just playing with this Newton's second law all the time, right? Because we're going to describe this system, that system in different coordinates. Now, next coordinates, the most popular after Cartesian polar. So let's adjust, let's rederive Newton's second law, but now in polar coordinate system. Okay, so oh, cylindrical basically. The same z-axis stays. I don't need this. So which way I label it? Okay, Newton's second law in two-dimensional polar coordinates. Right. Newton's second law in 2D polar coordinates. As I said, now foundation is underneath, and now we will just start exploring all possible situations, like applications of those fundamental laws, right? Okay, so first quickly, of course, in Cartesian we use x, y, in polar r, phi. Maybe I'll draw some picture in the middle, right? So y, x, if you take a point over here, of course you can define it using x and y, or you can use, of course, r and phi. Phi is measured, of course, from the positive x-axis in a counterclockwise direction, right? Oh, of course, you can change it, right? And very often, again, sometimes it's important to see the direction in which phi is increasing. And very often students don't like showing that, right? Sometimes I have to deduce, right? What's the direction of phi? Right? Or maybe I can draw this dash line. Then unit vectors. Those are troublemakers in this case, right? So they create all this mess with polar coordinate system. All right. R hat. Of course, you know, right? It's the direction of basically. R hat points in the direction in which we have to go in order to increase R, keeping phi constant. So phi is constant, you have to move that way, and in that direction R increases. So that's the direction of R hat. Then the same with phi. It points in the direction that you have to move, and phi increases that way, that you have to move in order to increase phi, keeping R the same, right? So it's they're perpendicular to each other, so that is phi hat and R hat. And of course the trouble is, if now your point is over here, right? So then your R hat will be that way, and phi hat will be that way. They're still unit vectors, but now directions are different, and that's the trouble of switching to polar coordinate system, because phi hat and R hat changes direction, and we have to take care of that mathematically. And that's what we're going to do maybe for the next 10-15 minutes. Take care of finding how R hat and phi hat changes in time. Right. Or maybe I'll show this is R. Right. And of course transitions are trivial, right? You know that x, if you want to find x, it will be r cosine phi. Why I used phi? Ah, yeah, I used phi, yeah. Y will be, of course, r sine phi, so basically transformation equation from r phi to xy, and of course the opposite direction, r equals square root of x squared plus y squared, and phi equals to arctangent of y over x, right? So you can move back and forth. Of course, you all know that, but it's worth of reminding. And so now, let me check if I mentioned. Okay, let me write that phi hat and r hat are not constant vectors. Right. R hat and phi hat, they change their directions. And here, of course, I will put a big sad face, because that's I would say disadvantage, but this coordinate system is very useful for those cases. This. Okay, so now this short introduction, and now let's get to the main question. Let's write Newton's second law in polar coordinates. Right. Again, so it's a mr double dot equals f. So now we need to write this down in polar coordinate system. And so what do we have to change? Okay, mass, it doesn't care where you are, right? Force, the same, actual force. Again, actual forces. We're not talking about some fictitious forces. That will be much later, right? Actual forces, it doesn't matter if you're in this coordinate system, in that coordinate system. They just act on your system, and you have to just write it in terms of your coordinates. In this case, you'll have to find phi component and r component of the force, right? That's it. So here, nothing can be done. So all the troubles are in r double dot. So we need to carefully take two derivatives of r vector r. Let me first write that f, of course, will be f r hat plus f phi hat. So again, so here nothing to do. R, maybe you know what. Basically, let me show that that's what we have to take care of. Right? And of course, what is r, vector r? It's a magnitude of r times r hat. So we just need to differentiate this twice. But of course, it will give us lots of, okay, not lots of, but a few terms. Right? So let's start with the first derivative. So r dot, okay? So it's r vector, and this is just a magnitude, so it will be r dot r hat plus r dr hat over dt. Here, r is our usually unknown, right? It will be differential equation, so we'll have to solve it. So here, nothing can be done again. This is r hat. That's what we don't know. Dr hat over dt. That's what we have to find. Right. Okay, and now I will probably draw a picture over here. Right. So now the question is about the r hat over dt. Or maybe I can squeeze it this here, this part. Yeah. No. So this is x, y. We usually start with Cartesian because it's kind of convenient, and then on top of that you can put whatever coordinate system you want to use. And let's assume that we have the point mass which somehow travels, and let's look at two moments of time, and sort of very close to each other. So they are apart by dt. So let's say first it is, for example here, let me follow the picture which I have. So let's say this is a position of the object at the moment of time t1. This is t1. Of course, our unit vectors are going to be, this is r hat at t1, and over here, of course, they will be, it's ugly. And this will be phi hat at t1. Right? Then after a moment of time dt, of course, the object will move somehow. Let's assume it will be over here. So this will be at the moment of time t2, and let me write underneath that t2 equals t1 plus dt. Usually I try to write it on the picture, but now I feel like don't have enough space. So that will be position of the object after dt, and now our vectors are going to be pointing, this is r hat. This will be our r hat, and this will be our phi hat. And of course the angle, so this is phi 1, this will be phi 2, and this is delta phi. Change in phi. Okay, now we want to find dr over dt, so let's just focus on only these r hats. So those r's I will redraw here, this r and that r. Okay, I will use the same color, blue, right? So this is our r hat at t1, this will be r hat at t2, and of course this will be delta r hat, and of course this angle this angle is equal to that angle, delta phi. So this is delta phi. A little bit of geometry. So now let's write down delta r in terms of just a small triangle with this small angle. So we can write this way. So delta r hat, I'm just looking at this picture. So it will be absolute value of this times the angle. So it will be approximately equal to absolute value of r and times delta phi. Right? And this is the vector. So we need to add a direction, because that is just the absolute value of this vector. But direction, if you draw properly, right, everything, you see a direction of delta r, it's a direction of phi. I think it's obvious, right? The direction of delta r hat, it's the direction of phi. So phi hat. Of course, absolute value of this is just 1. Oops. Is just 1. And then now what is delta phi? Since phi dot approximately equals to delta phi over delta t, so delta phi will be equal phi dot times delta t. Delta phi equals to phi dot times delta t. So we can plug this delta phi. As a result, we will have, let me rewrite it here, delta r hat approximately equal, so this is 1. Instead of delta phi, we have phi dot delta t. And in the phi hat direction. So we're almost there. So what again? We want to find dr hat over dt, so we need to take this, combine with that, and take the limit when delta t goes to 0. So now, difficult to write here, so I will take limit of delta r hat over delta t. Right, so again, this goes to there, and I'm taking the limit when delta t goes to 0. And of course, by definition, calculus, it's a derivative of dr hat over dt. And so what's left on this side, it will be everything is it's fine, but for some, no, I don't know why I started doubting myself. Sometimes it happens. When you're in front of people, sometimes your brain can panic a little bit. Right. No, everything is fine. So now what's left? Phi dot phi hat. Phi dot phi hat. So that's the derivative. So this equals to phi dot phi hat. So derivative of r hat with respect to time equals to phi dot phi hat. Okay, so now let's rewrite it over here. I will move the O can go here. I used it in physics 1 as the source of my electric field. I mean physics 2, not physics 1. So let me rewrite this. Right. So we completed the first step. So it's r dot equals to r dot r hat plus r phi dot phi hat. And you see well-known results. So r component of the velocity, it's r dot, and a phi component of the velocity, r phi dot. We used it all the time, right? Whenever we go to polar coordinate system, right? So we found velocities. But again, it's not the final goal. The final goal is r double dot. So it means we need to grab this equation and differentiate it one more time with respect to time, right? And now, of course, we'll get a bunch of terms. So let me check if I mentioned everything. Yeah. So now the next bullet. So now r double dot. So r double dot equals, it's a derivative of this. So d over dt of r dot r hat plus r phi dot phi hat. So now we have to be careful, right? Because it's so easy to lose something. Right. So r double dot r hat plus r dot. R dot, and I wrote r hat. R dot and then dr hat over dt. So I took care of this, and now that plus r dot phi hat plus r phi double dot phi hat, and the last term it will be plus r phi dot and the derivative of phi hat with respect to time. Bunch of terms. Now let's look at them carefully. Again, here nothing can be done. Again, it will be our second order differential equation. So r is unknown. We usually differentiate, integrate to find r at the end, right? The same, dr over dt we already found. Dr over dt we know it's a phi dot phi hat. Let me emphasize on that. So this is already we know. It's a phi dot phi hat. Then this is again nothing. Nothing can be done again. We will have to integrate in order to get phi also. Again, nothing, 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 d phi hat over dt. So this is now our major trouble. So we need to find that derivative, how phi hat changes with time. Right. Okay, and we're going to recycle the same picture. So here we took r hats and draw this picture. Now we're going to take these phi hats. I will draw over there in order to do very similar manipulations, right? Very, very similar. Right, so now let me emphasize that we're going to take care of d phi dot, d phi hat over dt, right? So that's, and you know what? I should have used different color. I don't know why. So let me use green. Right. So now I have to draw these green vectors. So it will be phi hat at t1. And this is approximately phi hat at t2. And of course, again, they are perpendicular to r hats, right? So it's just basically like taking this picture and turning by 90 degrees. Of course, the angle between delta phi, the angle between them is still delta phi, right? And like here, we use delta r hat. Now we need to draw delta phi hat. And of course, this is delta phi hat. delta phi hat. And again, using the triangle with that small angle, it's a side times the angle in radians, right? Right, so from here we can write that delta phi hat approximately equals, approximately because we're talking about deltas, not infinitesimally small things. So it will be absolute value of phi hat times delta phi, the angle, and the direction. Again, if you draw carefully, look carefully, you will see the direction of delta phi hat. It's a minus r direction. It will be towards the center, exactly towards the center. So, times minus r hat direction. The picture, from the picture. Okay, so now again, this is just one. Delta phi, we will use the same story. Phi dot delta t. And again, this is phi dot delta t. So as a result, we're getting phi dot delta t and minus r hat direction. The same. Now let's combine delta phi hat and delta t on one side. Take the limit. So limit of delta phi hat over delta t when delta t goes to 0. Of course, just a derivative from calculus. Derivative of the unit vector d phi hat over dt equals. And what's left? Negative phi dot r hat minus phi dot r hat. That's the derivative. Right. Okay, so now we have to go back to this bunch of terms. Let's rewrite them carefully, substituting, making all these substitutions, because now we have to be careful. I have to be careful, right? Because it's so easy when you start rushing it. Make some silly mistakes. Right? So, back to our double dot now. So our double dot will be, okay, I'm just rewriting all this. So first, r double dot r hat, then r dot phi hat, r dot phi hat, it's this term, then exactly the same term, r dot phi hat. But anyway, let me write all of them. R dot phi hat, it's this one, then r phi double dot phi hat, and now they will be with minus, so it will be r phi dot squared minus r phi dot squared and r hat. Whew. Now let's combine them. But now it's time to make them look nice. Make it look nice. Right, so what do we have? R hats. We need to combine that. Those. And phi hat in the phi direction. Right? So as a result, finally we're getting basically the final result, so, which we wanted. R double dot equals. So first r hat. Radial acceleration, r double dot. Then r phi minus r phi dot squared. Centripetal acceleration towards the center, right, as we remember. And now in the phi direction. Okay, let me first write this in the order of importance. Tangential acceleration in the phi direction. And the second, this 2r dot phi dot, that's Coriolis acceleration. We will discuss it, of course, when we move in chapter 9, I think, when we start discussing non-inertial reference frames, right? But again, we will get something similar, and then we will decide how we're going to treat it, right? Okay, I can emphasize that this is Coriolis acceleration. But we're not going to use it for now. Until chapter 9, we're not going to use it. Right? The rest you're familiar, except for that. Right? So let me check. I think in this now, yeah, we just need to actually write down Newton's second law. We just need to combine. So r component with acceleration times m, and that. So finally, Newton's second law. You see how much we sweat in order to rewrite Newton's second law in a reasonably simple new coordinate system, in polar coordinates. In Lagrangian formalism, you don't have these troubles. You just grab the same equation, Lagrange equation, just change coordinates. Instead of x, r, instead of y, phi, and that's it. The structure of the equation is exactly the same. That's a significant advantage. So as a result, so we can write m r dot double dot minus r phi dot squared must be equal to the f sub r. Of course, net. That's the net. All components in the r direction. Components of forces. Then m r phi double dot plus 2r dot phi dot equals to sum of phi components of all forces. Right. So, and of course, you can imagine if you do decide to use some elliptical coordinates, right? Of course, you can get that from the books, but strictly speaking, of course, you have to spend lots of time making a transition. Okay, so now we have Newton's second law, the equation of motion written in Cartesian in polar coordinates. Now let's just quickly look at one of the examples, and I guess that's where we will have to stop. Simple case, skateboard park, semicircular shape over sort of like a trough, and the skate can move back and forth. So we need to write down the equation for this motion. Of course, since we have cylindrical symmetry, right, of course we're going to use polar coordinate system. And of course we're going to introduce phi, and so on. And I guess I have to move here, right, I just need this. That's it. The rest we all know. Yeah, I can erase this.
So it's called a half pipe.
Oh yeah, half pipe. Yeah, half pipe. Thanks.
Yeah.
Thanks. Yeah. Right. I didn't look at my notes, so I was trying to come up with explain it in my words. So it's example 1.2 actually. I was surprised how much of words Taylor managed to produce explaining this example. It's too much. So okay, let me just label half pipe. Is it hyphenated? Yeah. Half pipe problem. So what is given? Radius. Actually, there is the number, but I don't care about numbers. I don't like plugging numbers. It's one of my least favorite thing to do. Right. So, half pipe. Finally, I can use this. Alright, again I will draw also Cartesian because it's convenient to first draw Cartesian and then on top of that draw the rest. Right, so this will be yx, but of course we're not going to use it. Of course we're going to use polar coordinates. So let's assume that the skate is, for example, here. So that's our skate. Right, so this is r, but of course which is constant, right? R small equals r, and oh yeah, it has some mass, but you know what? I don't want to write mass. This problem is actually important to show from which direction phi increases. In this case, I decided to measure phi from this direction. So phi, no. That's the bad thing to write. Phi increases that way. So it means what? It means that phi hat that way. So that's my phi hat. R, there is only one choice. That is r hat. Right. Actually, no, I shouldn't have used red. Usually I use red color to draw forces. Right. Okay, I have to flip the colors. So then, of course, we will have to identify all forces. Nothing. Everything is trivial. So this will be normal. This will be gravity, mg, right? And of course, this angle is also phi, right? So this is phi, right? So now, r is constant. R equals to r capital is constant. So of course, r dot equals to r dot equals to 0. So this gets evaporated. So as a result, we'll have first equation in the r direction minus m r capital phi dot squared equals to, okay, r components of all forces. Normal is in the negative r direction. So here we have to be careful in terms of these pluses and minuses. So let me start with this because I like to start with positive. So mg times cosine of phi, it will be in the positive r direction. So it will be mg cosine phi with plus, and then of course minus n. Newton's second law in the r direction, right? We applied. Then in the phi direction, that is 0, so there is no Coriolis acceleration, only tangential acceleration. So it will be m, again r capital, phi double dot, and now all forces in the phi direction. And of course, we have only one force. This component of the gravitational force. And that component will be in the negative phi direction. So that goes, it will go into the equation with minus. It will be mg sine phi. So it will be minus mg sine phi. So that's the system of two equations which we have to solve. But yeah, first of all, mass distraction can be done in the second equation, right? So this m and this m can be cancelled. And so they basically semi-coupled, because the second equation basically decoupled. But in the first equation, of course, you need the results of the second equation, right? So, of course, two unknowns, n and phi. So the second equation you should be able to solve, find phi, and then plug it in the first equation to find n. But since the question is not about finding n, forget about the first equation. But you understand the idea. So, okay, so they are partially coupled. Partially coupled. Right? So, which is good. Right, so as a result, let me just rewrite the second equation. Since we are interested only in the description of motion, we're not interested in the normal force. So it will be plus g over r sine phi equals to 0. Of course, this equation cannot be solved analytically. Right. Of course, we're going to introduce, instead of g over r, omega squared, following the trend. Right. And we're going to assume, of course, otherwise it's impossible to solve, assume phi is small. So we're going to assume make a small angle approximation. So we're going to make a small angle approximation. Right, so phi double dot plus omega squared phi equals to 0. So we're getting simple harmonic motion equation. I stopped solving this equation because we're going to spend quite some time in chapter 5 discussing all the solutions for this equation. So right now I'm just going to write down the solution, of course you know. So of course phi in two forms I can write. So A cosine omega t plus B sine omega t, one option, or you can write phi, for example, C times cosine omega t plus delta. We're going to get all the solutions in chapter 5 when the whole chapter will be dedicated to all oscillations, right? Not coupled, just simple single object oscillations. Okay, I'm not going to apply any initial conditions, right, like your book does. You've done it. It's not the major point. Right. And as I said, book discusses this equation in details now. Okay, so we can call it a day at this point. So next class. So basically, we already introduced conservation of. No, I'm blocking this. No, I'm blocking that way. I'm seeing myself on the TV on screen, right? Because in Physics 2 class I use green screen effect, so I need that TV. So also I can see it here. Next class, since we introduced conservation of linear momentum, we're going to spend pretty much the whole class discussing a motion of a rocket, right? So basically, again, you see now we start applying fundamental stuff which we presented the previous class mainly, right? In order to discuss this system, that system, and then we'll start looking for possibilities of simplifications of our life, right? And we will move into the energy approach. But next class, rocket equation, right? And a couple of examples, problems. There will be in your homework a couple of problems of that type. But rocket equations are not going to be in your first homework. This, yes, in the first homework there will be some cylindrical system, right?